Okay, so we are continuing. This is the second part of our series on metallurgy. Previously, we discussed about, for the most recent part that we discussed in a previous video, it was basically about how the blast furnace process works for the production of iron. So, you started with an ore. Now, you have molten iron and molten slag. So since the iron at this point is said to still contain a lot of impurities, you call it pig iron or cast iron. Properties include it has a really low melting point and it can be cast to different shapes and forms. So yeah. So where did these impurities come from? So while you introduce the iron ore with the limestone and coke in the furnace, so the limestone basically contains CaCO3, and when you roast it, it forms CaO, and this reacts with the impurities found in the ore. So silicon, SiO2, and Al2O3, both of which are solids. So when CaO reacts with these impurities, they constitute what is considered as part of the molten slag. So these are molten impurities that you want to separate from the molten iron. The molten iron, since it has a higher density compared to that of the molten slag, it's usually it situates itself at the very bottom of the furnace. So you can collect it from there, essentially. Okay, so moving on. So iron could be used later on in steel manufacturing. So this is you can carry out this process via the oxygen process. So from oxygen, you can call it, or you can classify it as an oxidation process. So this is one of the easiest and fastest methods for steel production. So you're basically converting iron to steel. So steel is an iron alloy that contains less than 1% to 2% of carbon plus other impurities. So you can say that this is almost considered pure iron compared to iron earlier, which was characterized by having a significant amount of impurities. It's opposite than that of steel. So the percent composition of steel has to depend on its purpose. So depending on where you're going to use that steel, the properties with respect to percent composition may be different. So I'm not sure what this let's say it's a capsule. I'm not sure what it's formally called, but we're still talking about a blast furnace. Okay, so this is the poured molten iron and the slag. So it is still in liquid form. So if you introduce oxygen to it, and oxides form. Pressured oxygen is introduced into the container, and CaO or SiO2 is placed inside. I'm not sure what this means or what it implies. It says here to form what? We might find out later. So this is in vertical position. In horizontal position, this technically is the slag. Again, molten steel's density is greater than that of the slag. That's the reason why molten steel lies at the very bottom. So this time, it has been more purified. So molten steel can be sampled at different time intervals to check the percentage of iron and of other impurities. So yeah, um, once you have the percentage composition that you want, that vessel is moved to a horizontal position. Okay, it makes sense. So coming from here, you uh, you make it lie down. You make the vessel lie down to a horizontal position. The composition of steel depends on the temperature that is used when the process is done. So at extremely high temperature, um, molten molten steel, or basically iron, when you combine it with carbon, you form iron carbide. In other words, you can call it cementite. And molten steel sinks because it's denser, so the impurities just float. Impurities which are found in the slag, I believe. Or at least you can think of it that way. Impurities are not dense, so they are found above the molten steel. Why does it keep going like that whenever I try going down? Bruh. Anyways. Okay. So if you cool rapidly, so now that you have the iron carbide, it remains as is. So there is no chance of separating. I'll continue on this later. Let's go here first. So depending on the temperature, the chemicals involved, and how fast or slow you cool a material, you can control the amount of carbon that is present as graphite and as cementite. So to control whether you have more or less graphite on the surface of the material, you can perform what is called as tempering. So essentially, if you quickly heat steel and you cool it rapidly, this produces more cementite and more graphite. In a similar perspective, if you cool slowly the iron carbide, it can reverse back to iron and carbon. Ideally, this is what you want to happen. If you cool slowly and carbon is separated from iron carbide, this carbon separates as graphite on the steel's surface. So the only challenge here is how you'll be able to memorize or connect the dots now that you know the information that you have to know. Sorry. Okay, let's go to the types of steel. So we have three types: plain, high strength, and stainless. For plain type of steel, the amount of impurities is extremely high. Maybe not extremely, I might be exaggerating. Just know that impurities are quite a lot in comparison to the other types that will be mentioned here. So there are large traces of carbon and manganese, really small traces of phosphorus, sulfur, and silicon. What's the purpose of this type of steel? Plain steel for sheet products and tools. For high strength type of steel, there's a low amount of carbon, a high amount of manganese. So what's the purpose of this? This is for construction and steam turbines. The uses or the purposes are just not limited to these two, of course. The same thing goes for every other type here. Just to give you an idea, I wrote down a few purposes for each type. For the third type of steel, stainless, it has large traces of silicon, nickel, and chromium. I believe this is chromium. There are also small traces of carbon, manganese, phosphorus, and sulfur. So these are for kitchen utensils and razor blades. So usually when you don't want these tools to stain, especially, it's very crucial. Razor blades, they come in contact with the most delicate parts of your skin. So if it's stained, if it's not clean, you're basically cooked. Especially if the razor blade causes a cut or a wound. You don't want that to happen. And for kitchen utensils, you use them for food. What if the tools are stained? Right? You get the idea. Okay, so let's talk about purification of metals, the techniques. Metals prepared by reduction. So again, you need to reduce the metals. For what purpose again? It's been mentioned here. Okay, so not all compounds are reducible. You have to undergo preliminary processes first in order to convert an ore to a more reducible chemical state. I don't think I answered the questions that I just said, but yeah, it has something to do with being reduced. So from there, you can it would be easier in a way to get or extract the target metal from the ore itself, and it also has something to do with purity. Okay, so yeah, metals prepared by reduction usually needs further treatment in order to remove other impurities. So the extent of purification will depend on how the metal will be used. So if you want pure iron, there are three techniques: distillation, electrolysis, and zone refining. For distillation, this is only based on boiling points. So metals with low boiling points can be separated from a metal mixture through what is called fractional distillation. So yeah, tube with different layers by temperature. One application, I'm not sure if that's the correct term, but we have something called the Mond process for the purification of specifically nickel. So nickel plus 4 carbon monoxides produces nickel carbonate, I'm not sure, NiCO4. So this is very volatile. In other words, it has a low boiling point. You boil it off, collect the vapor in a separate vessel, and then you condense. So upon condensation, after 200 degrees Celsius, you have pure nickel, and for carbon monoxides, it's somehow, from here you can say that there's a cycle, because after producing pure nickel at the same time, you produce carbon monoxide that has been produced earlier. Carbon monoxide is also produced, which could be used for well, creating more pure nickel. So yeah, you get the idea. You might ask where this comes from. It should come from previous purification processes. Okay. The second technique, electrolysis. So this is when you want to achieve around 99.5% purity. So this is not, because there's another technique, I'll spoil it to you already. For zone refining, this is when you want to achieve 99.999% purity. That's when you choose zone refining. But for just 99.5%, you choose electrolysis. For distillation, I'm not really sure. It hasn't been really specified by my professor. So the copper metal obtained by roasting CUS usually still contains metal impurities. So roasting basically will not suffice. And because there are different metals in this ore, the standard reduction potentials are they vary, or you can call it assorted, because again, different metals have different standard reduction potentials. So how can you say, how can you justify that a copper metal is pure when it has various standard reduction potentials? When you say it's pure, there's only just one kind of metal in a sample. So you separate them by electrolysis. So from an impure anode, copper, copper, by the way, is a reactive metal. So you oxidize it into copper ions, which can dissolve into the solution. So they are not reduced at the cathode. This is the illustration of electrolysis. So beaker, you have the beaker. I believe a beaker would suffice. You have a battery, impure copper anode here, the pure copper cathode at the right side. This one is sharp, unlike the one at the right. It has something to do with copper dissolving. So the anode and cathode are immersed in a sulfuric acid solution to give us the sulfate ion. I believe this is sulfate. So yeah, once copper is reduced, it will form copper solid. Let's have that sink in first. What's been mentioned earlier. Let me just drink water. Okay. So I know that the explanation here isn't that clear yet. In that case, if I were you, I'll just search third-party resources aside from this video. Yeah, that's what I'll do also after this. I can't not understand this. Never mind, but I just double negative. Anyways, so once copper is reduced, it will form copper solid. So when you when you undergo reduction, so in the reactant side there are electrons. So the positive here will be removed, so you just have Cu, or just copper, no charge. And this copper solid is deposited on the cathode's surface. So the less electropositive metals are not oxidized, so basically they only remain as solid impurities. What we're only talking about here, what applies, are the more electropositive metals, to which silver and gold aren't one of them. Okay. Okay, we're close to the part that I don't really like, band theory. Anyways, the third technique is zone refining. So this is used in order to obtain extremely pure metals. I've already mentioned this earlier, just in a different way. So if you want to achieve 99.999% purity, you resort to zone refining. So what happens here is basically metal is passed through a heating coil. There is no drawing here, but just search on it. You'll get what I mean while I explain it. So metal is passed through a heating coil, and the metal melts. Impurities will stay at the molten part, basically. And once the heated portions of the metal cool, in theory, that's supposed to be pure already. But of course, realistically, you can't say that after just the one round, uh, the heated portions are already pure. And that explains why we repeat this process multiple times. So, essentially, in every round, impurities are concentrated at the end, at the last portions of that piece of metal. So, in response to that, you just cut that off. Okay? So, that's basically it. Um, it's not hard to understand. Sorry. Okay, chemistry of metal. So we're done in metallurgy itself. Let's look at the chemistry part of it. So metals are again, what's easy to understand is that they are good conductors because they have high electrical conductivity. So in the band theory of conductivity, this essentially is one of the models that's used to study metal bonding. So essentially, delocalized electrons move freely through bonds that are formed by overlapping molecular orbitals. Okay, here we go. Just a disclaimer: I won't be able to explain this with my own words. This definitely is one of the hardest parts for this test. It's not easy to get. Okay, this can be applied to conductors and just some elements that are considered semiconductors. So, an example that we're citing here is that of magnesium. We have its, what do you call this? Electron configuration here, as well as its configuration as if we express it as neon. I know there's another way of expressing electron configuration. I think it's called noble gas configuration. So this is one way of expressing it. So each atom of magnesium has a valence of 2 electrons in the 3s subshell. So that's very specific. In a metallic crystal, atoms are packed close together. So energy levels of each atom is influenced by neighboring atoms. The metallic crystal will look like an array of positive ions swimming in a sea of delocalized electrons. What has been mentioned earlier, this delocalized electrons, that's the one here. So yeah, energy, conduction band, valence band. More on this later. In a way, I don't really get this illustration, but in the next page, I kind of get it. How the bands are applied. So yeah, it's just the band theory that I don't really get right now. A strip of magnesium contains billions of magnesium atoms, so molecular orbitals will also be very large. These molecular orbitals are closely spaced, that's why they're called bands. Okay. Energy gaps between valence and conduction bands in metals, semiconductors, and insulators. So, in a metal, this is what the illustration looks like. So, the conduction band is here, the valence band there. Actually, that's standard. Conduction band where energy is higher, valence band where energy is at its, that's where you start, right? So, in a metal, electrons can freely travel through the conduction band. So, this basically explains why metals are really good conductors. And increasing the temperature makes the metals less effective as conductors. So, that's one thing you'd like to know. the higher the temperature, basically atoms vibrate. So that's what happens. For semiconductors, um, I believe this has been mentioned in the previous topic. So one example is silicon. Silicon, which is used in making transistors and solar cells. So semiconductors, we have this illustration. So unlike the previous illustration that we saw, we have an energy gap this time in the middle. So you need to apply a certain amount of energy so that electrons would be allowed to jump from the valence band to the conduction band. So because of this energy gap, you need to apply a certain amount of energy. And this is only the condition such that electrons can travel freely. So if there is no energy that's applied for the jump to take place, electron movement cannot be made possible, considering it has to go from valence to conduction band. So, if you apply heat to semiconductors, this, unlike metals, it actually makes them more effective semiconductors. Heat can be translated as energy, right? So, this can bridge the energy gap. So, it's not hard to understand semiconductor in contrast to the metal in terms of how they respond to heat. So, for insulator, on the contrary, we have examples, glass and wood. So, the energy gap is just really large. So, it is safe to say that mic test check. Hello. Anyways, when you apply a certain amount of energy, well, it's just pointless because again, the energy gap is just too big. Okay. A semiconductor's ability, so the one here, its ability to conduct electricity can also be improved through doping. So on top of this condition, its capability to conduct electricity can also be improved through doping. This is the process of adding small amounts of certain impurities in the material. So for example, phosphorus and aluminum can be added to silicon. So yeah, there are two types of semiconductors that you'd want to know. So the N-type and the P-type. The N-type semiconductor, it contains donor impurities. So phosphorus, for instance, has one more extra valence electron. This can covalently bind to 4 other atoms. So in this visual illustration, we have phosphorus in the middle. It can covalently bind to 4 other atoms. So once excited, electrons will jump to another silicon atom. Silicon, by the way, again, like I said, phosphorus and aluminum can be added to Si as a form of doping. The process of doping taking place. So phosphorus in the middle, silicon everywhere else. So electrons will jump to other silicon atoms. Only the presence of an electron can already start the electron movement or flow in the semiconductor. And in the P-type semiconductor, this basically contains acceptor impurities. So we have aluminum as an example. It has 1 less electron. So that's a difference compared to what's described in an N-type semiconductor. So here, in an N-type, phosphorus has 1 extra. Here, in P-type, aluminum has 1 less electron. So it is possible to excite an electron. Once excited, it can be transferred to the positive hole. So in this way, the electron is moving and conducting electricity. Okay, so let's go back to this characteristic. Aluminum has one less electron. So here in this illustration, you can see it only covalently binds to 3 other silicon atoms. So just know this characteristic connects to this. Therefore, it has a positive charge showing one vacancy in its bonding orbital, the positive charge over here. So if it's positive charge, automatically you know it's p-type. And yeah, acceptor impurities are electron deficient. Because again, there's a positive charge, so it makes sense that they lack electrons. Because electrons are the ones that contribute to the negative charge, or basically reducing the amount of positive charge. Okay. Next. Okay, I think this is my favorite part. Trends in metallic character. So, I think this has a positive relationship with electropositivity. That's very important in our lesson. I'll just have to confirm it. Relationship between metallic character and... Oh, okay, that's good. Electropositivity. Okay, so it is confirmed. Metallic character, which is described to be the trend going down and going left. So basically, geographically speaking, you're going southwest. So it is said to be directly proportional to the electropositivity of an element. So that's good. In the same vein, you could say that the trend, or basically metallic character, has an inverse relationship with electronegativity. Again, fluorine is the most electronegative element. I think I mentioned that in the previous vid. But yeah, so it makes sense for its inverse, which is metallic character, to be in the opposite direction. So going to the left and going down. I want to know, what is the most electropositive element? Cesium. Is cesium a metal? It is an alkali metal. Okay, it makes sense. Cesium is located here, technically in group 1, alkali metals. It's considered an alkali metal. Okay, so yeah, it's somewhere here, just below francium. Let's not mess with the radioactive elements. Francium is under cesium. There's a reason. There has to be a reason why it's not considered the most electropositive. Okay, so I think in general, we stay away from radioactive elements in the context of our lesson because they are radioactive and it's difficult to study them in bulk. I remember that's the same reason our prof said in a similar conversation. So going back, pure metals are often shiny and they are solid at room temperature. Of course, an exception is mercury. In the case of mercury, it is liquid at room temperature. Metals are good conductors of heat and electricity. They are malleable, they can be drawn into wires, and they have low electronegativities. Like I said earlier, uh, metallic character has an inverse relationship with electronegativity. So the more, let's say, metallic-ish it is, uh, it has a lower electronegativity value. So it explains why they are often positively charged. Where has this been mentioned previously? Actually, in the first page. Metals can have positive oxidation numbers. So they can be separated from their combined forms through reduction process. They have to undergo reduction for so that they could be produced. So yeah, originally they are positively charged. I want to talk about two groups of metals. So we have the alkali metals and alkaline earth metals. For alkali metals, the oxidation number always is +1. This group is technically considered as having the most electropositive elements. Logically, because again, like I said earlier, cesium is located here. It's technically considered an alkali metal. And yes, at the same time, consequently, they are the least electronegative. They have low melting points, low densities, wherein lithium, I believe lithium is below hydrogen. It is the lightest known metal, and this is actually the reason why batteries, it's ideal to use lithium as the component for battery production. It's kind of because of their weight. They're pretty light. And yes, they are highly reactive. So you need a licensed chemist with you if ever you want to experiment with lithium and water. Just with the right amount of lithium, you can create an explosion. So they're often explosive, essentially, when in contact with solvents such as water. For alkaline earth metals, the oxidation number will always be +2. Wait lang. Let me just confirm if oxidation number and ionic charge are the same. Or if they're not the same, they're definitely directly proportional. Okay, so oxidation number is just a hypothetical charge, but ionic charge is the actual charge of an ion. Okay, I think that's enough to know. Oxidation number is just hypothetical. For ionic charge, it's the actual. So, unlike group 1, alkali metals, group 2 is characterized by having higher melting points. Therefore they are more costly to process energy-wise. It makes sense because if something has a higher melting point, you need more heat so that it could melt. And more heat means more energy. That means your electricity bill would be higher. So, yeah. It is somewhat less electropositive. Somewhat only. Because, again, in terms of the trends in metallic character or electropositivity, the more you are on the left, the more electropositive you are. But in the case of group 2, it's at the right side of what's at the most left of the periodic table. So, you get what I mean. And yes, it is less reactive than group 1. Except for beryllium. Kind of the same reason why earlier francium isn't considered in the comparisons for electropositivity. Although hypothetically, francium is considered very electropositive. It has radiation. So in the same kind of idea, radium, which is located in group 2, is not included in the studied properties because its isotopes are radioactive. Therefore, they are difficult and they're expensive to study. So, okay, we're done with the first two groups of the periodic table in terms of the context of metals. Let's talk about aluminum. Aluminum is considered as the third most abundant element on the Earth's crust. So, coming from impure aluminum oxide, which is found in something called bauxite, when you heat it in hydroxide, it produces aluminate ion and water. So, it is important to know that pure aluminum doesn't occur in nature. Therefore, we have to extract it from our bauxite. Bauxite, I've already mentioned that earlier. So it contains something that we need to know, that is Al2O3. Okay, we've already gone through this equation. Next, this aluminate ion undergoes acid treatment, and basically aluminum hydroxide is filtered out. This aluminum hydroxide, when heated, returns back as aluminum oxide, Al2O3, and water is also produced. From here, aluminum oxide is reduced in order to produce aluminum using something called a Hall process. So the aluminum oxide is then electrolyzed in order to form aluminum and oxygen. Then the aluminum, which is a solid, sinks to the bottom, becoming ready for collection. So yeah, essentially electrolytic reduction is performed. You electrolyze aluminum oxide. To visualize, this is what it looks like. The whole electrolytic cell, we have the carbon anodes and the carbon cathode here. Aluminum oxide in molten cryolite. Cryolite is the solvent of the aluminum oxide. And the solid aluminum that has been mentioned here, after being electrolyzed, it's characterized to be molten. So the molten aluminum sinks to the bottom, ready for collection. Okay. What's the anode and cathode here? Molten, so aluminum is liquid, right? So aluminum in its liquid form as a product of the cathode. In the anode, oxygen. This is not oxygen. This is oxide, I think. Yeah. You produce oxygen and electrons. Aluminum plus 3 electrons makes aluminum liquid, or basically molten aluminum. So 2 aluminum oxides produces 4 aluminums and 3 oxygens. Okay. Okay, let's continue. Aluminum is a very versatile material. It has low density, high tensile strength. It's very malleable. On top of it, it's very cheap. It's very affordable. It's also a good conductor of electricity. Also, I think copper is still better in terms of conducting electricity. More on that later, actually. Aluminum, in connection to what I just said, it could be used for something called voltage transmission lines. So it is proven that copper is a more efficient conductor, but aluminum is much cheaper and lighter. Aluminum could be alloyed with other metals, copper, magnesium, manganese. They could be used for airplane construction. Okay, going back here. Yeah, I already said it. Tapala. Aluminum is much cheaper and lighter. So there's this argument before. Actually, gold is a better conductor of electricity compared to copper. But of course, because copper is a lot cheaper compared to gold, copper is used. But there are cases when Even copper is already expensive itself, and that's where aluminum comes in. Also, I'm not saying that aluminum is technically appropriate as a perfect substitute for aluminum in certain applications in engineering. So I'll leave it at that. So 2 aluminum solid plus F2O3. This basically is called ceramite. F2O3, by the way, is hematite. It's a kind of iron. It's been mentioned earlier. Here, actually. Here, hematite, F2O3. So it's one of the kinds of irons that you, well, that's what you usually extract coming from an iron ore. So in a blast furnace. Okay, so basically aluminum plus hematite makes up what's called as thermite. When it undergoes 3000 degrees Celsius, or when you heat it at 3000 degrees Celsius, it becomes aluminum oxide and 2 iron. The change in heat is, I'm not sure about this one anymore, but it's just that negative 822.8 kilojoules per mole. Aluminum essentially has a great affinity for oxygen. So when you combine it with the transition metal oxides, for example, ferric oxide, to form a ceramite mixture, when you heat it, it can reach temperatures of 3000 degrees Celsius, the same value I mentioned earlier. Aluminum is also a relatively safe element. It is non-toxic, it's odorless, it's tasteless, and it's lightweight. So from this idea, it makes sense that it is an ideal material for the production of basically cans that contain the drinks that we consume. What I have in my mind right now is the pineapple juice from Del Monte. I think that's one example. So, well, it's just not limited to drinks. Possibly canned goods, canned food. So they're also made out of aluminum. Since it's also thermally conducting, it can conduct heat. Basically, drinks could be chilled rapidly when you put them to a fridge. So that's one advantage that comes along manufacturing drinks that are contained by aluminum cans. One drawback, though, is that aluminum waste has become an environmental problem. So, just like plastics, you see aluminum everywhere, almost. Whether you're in the supermarket, whenever you see waste, that's basically in your community, in some areas in your community. So, because it's very cheap, it's very commonly used in industries. So, the solution to this is basically recycling by melting aluminum waste, which is mostly just cans and foils. Although, of course, just not limited to these, for the purpose of making new aluminum materials. So you do this instead of processing bauxite ores. So it's basically going from step one again. We don't know how much bauxite ores are left. I know there's still a lot, but when you consider sustainability, it's more practical actually to just recycle aluminum waste by melting them to produce new ones. The same idea could be applied to plastics. I'll be making a video on that as well, on plastics specifically. And yeah, one benefit to this solution is that it saves energy. Again, it's expensive to process ores in general. So when you try to process ores that yield aluminum, it's basically unnecessary energy in certain circumstances when supposedly you could just recycle aluminum. So that's basically it. Thanks for watching.